First, I would like to say hello to everyone. My name is Maruša Matko, and I'm a PhD student at the Josef Stefan Institute. And I prepared this presentation together with my supervisor, Professor Kontić, who is here today, and with my co-supervisor, Professor Mojca Golubić. Our research is focused on how to include risk assessment into spatial planning, and today I'll talk about consideration of extreme weather events in spatial planning of energy infrastructure. The research is a part of coordinated research project under coordination of International Atomic Energy Agency. First, I will present a method that we developed for integration of risk assessment into spatial planning, and then I will show how this approach was tested and applied in 2 case studies in Slovenia. First is about risks to power lines due to ice storms, the event that was mentioned before. And the second one is about risks to hydroelectric power plants due to heavy rain. For the conclusion, I will talk about our further plans for the research. So, extreme weather event can cause direct damage to energy infrastructure, and it can also cause damage to the environment, which can then lead to additional damage to energy infrastructure. In case of the fallen trees onto power lines, for example. In order to prevent losses, it is rational to include risk assessment into early stages of development planning, so that we find locations where the infrastructure would be less vulnerable to specific extreme weather events. The method that we developed consists of 4 steps. The first is determination of geographic scope and intensity level of an extreme weather event, and it is based on data about past occurrences of the events. The intensity of each event is presented on a GIS-based map and evaluated on a scale from 1 to 4, where 1 represents the lowest and 4 the highest physical burden. The next step is analysis of vulnerability of a system. This means vulnerability of electric energy infrastructure and vulnerability of the environment where this infrastructure is situated. Vulnerability of electric energy infrastructure in terms of primary damage can be assessed based on engineering standards and building codes, but factors that cause environmental related vulnerability are more complex. In the first case study about ice storms, damage to forest has been used as a determinant of environmental related vulnerability, and in the second case study about hydroelectric power plants, we used model of soil erosion potential in watersheds to assess a potential secondary damage to hydroelectric power plants. The third step in our method is assessment of probability or frequency of occurrence of the event. The frequency is calculated based on historical data. Each event is then drawn on map and evaluated as in step 1 on a scale from 1 to 4, where 1 means the lowest frequency and 4 the highest. All these steps are then integrated to obtain risk index of each event, and these combinations are similar to ordinary risk matrices. I will now present how this approach has been applied. In the first case study about risks to power grid due to ice storms, we first gathered all the available data about past events and damages that they caused. This is shown in this table here. The data about icing events recorded by Slovenian Environment Agency ARSO is available since 1961 and we obtained data about damages from the archives of transmission and distribution companies, as well as publications in media. Each event was drawn on map and then categorized into category of intensity as well as into category of frequency. Here are criteria for categorization of the events, and this is the summary of categorization. Then intensity and frequency of each event were combined, as shown in this table. And also here you can see this in the last 3 columns of the table. So the drawn events were overlaid one atop another, and that's how we obtained the final result, which is a risk map. The risk map was first compared with Slovenian building code for building overhead high voltage power lines. And this building code divides Slovenia into 3 zones based on expected burden due to glaze ice. In first zone, which is not represented here, little burden is expected and damages seldom occur, while in the second and third zones we have relevant burden that can cause significant damage. As you can see from this map here, it would be wise to make revision of standard and maybe expand zone 3 and zone 2. In the next step, we compared 2 alternatives of planned high voltage power line from Divača to Beričevo, and we found out that the southern corridor of the southern alternative is a much better option because damages here would be significantly lower than in the northern corridor. So our next study is about risk to hydroelectric power plants on the Sava River due to heavy rain. Heavy rain can cause high discharges and increased amounts of floating debris and suspended matter in rivers. This can lead to interruptions of operation of hydroelectric power plants, and we gathered data about these interruptions on the Sava River. So based on the duration of these interruptions, we calculated how much energy was not produced and then how much this would cost. And then these costs were categorized. We connected these interruptions with discharges at different gauging stations on the Sava River because hydroelectric power plants are relatively new and we only had data available about interruptions since year 2000, but the gauging stations are in operation since 1926. So with this data we could calculate frequencies with greater certainty. For each event, categories of damages and frequencies were combined to obtain risk index. And this can also be seen here in the last 3 columns. Similar analysis was carried out for 2 other Slovenian rivers that have large hydroelectric power plants. These rivers are Soča and Drava. And risk indexes were calculated on the levels of the whole watersheds. And then this map was overlaid with a map of potential of soil erosion, as this is shown here. As you can see, damages due to interruptions of hydroelectric power plants would be lower on the Soča River than on Sava and Drava. But for Mura River, where we have a hydroelectric power plant, but none exists so far. It would be useful to obtain data from the Austrian part of the river, what happened with interruptions there. So the next steps in our research include first, risk assessment of other extreme weather events, for example, heavy snow, strong wind, hail, as well as assessment of other infrastructure, for example, photovoltaic panels and wind farms. We also plan to integrate risk assessment into spatial planning. In case study about power lines and glaze, I showed analysis of existing plan, but we will use the results of risk assessment in earlier stages of planning, that means in preparation of alternatives. A part of this analysis has already been done, and it is presented in our poster that is hanging in the lobby, and I will be happy to provide any further information to those who are interested after the session. Another thing we still plan to do is consideration of risk assessment results in maintenance planning. One case of good practice in Slovenia was adjustment of the intake facility for cooling water at the nuclear power plant Krško. As you can see from this table, the first two lines that are dark red, these are interruptions of nuclear power plant, which happened due to clogging of the intake facility for the cooling water. To prevent this, they adjusted the facility so that the water doesn't run to the pumps frontally, but from the sides. So we plan to analyze protective measures for other types of infrastructure and other events. So this would be all from my part, and if anyone has any question.
Great. Thank you. Thank you very much.